In this situation, we have a thin rod of length h and mass m on a frictionless surface, and it pivots around the one end. And what's happening, it can rotate freely, and the rod is at rest, and some ball is going to come up, and it is going to strike the rod perpendicularly. We're going to let the initial linear momentum, so that would be your p-value of the ball. So we have m times v. We're just going to call that p1. So this right here, the linear momentum is p1. We're going to let the final linear momentum be represented by p2. So that's after the collision. And our goal is to find the angular momentum of the rod after the collision. All right. So let's take a look at all scenarios, right? So what we have here is initially only the rod is in motion. So we have our initial angular momentum is going to equal our final angular momentum, but only the ball here, only the ball is in motion, so that's the ball. But afterwards, we need to take into consideration the rod and the ball. All right, so if that's the case, the angular momentum is going to be P1 times the radius. So that's our MVR, and that is for a point mass, because this is a point mass here. Afterward, we have LR plus, and then the momentum of the ball afterward is going to be P2R. All right, and what we're trying to do is figure out, well, in these situations, we're changing and looking at this momentum of the ball after. So sometimes it's going to rebound, sometimes it'll stop, sometimes it'll continue in motion. And so what we're trying to do is say, how is this changing as a result? So if that's the case, we're going to actually be solving for LR all the time. So that means that the angular momentum of the rod is always going to be P1R minus P2R. And we're trying to see how does P2 change as a result of the ball after the collision. All right, so this is what we're really looking at for this particular example. Okay, so I know that the angular momentum of the ball is the difference between the two angular momentums of the ball before and after. All right, so the first situation, what's happening is we have a ball that rebounds along its original line of motion. So what's going to happen is the ball coming up, and then it bounces backwards. Okay, now here's the thing. Linear momentum has direction. So what this is going to look like then, so we have P2, it's going to, it moves in the opposite direction. Which means then that the angular momentum of the rod is going to be P1R minus, and now I have the opposite direction of what we have for our linear momentum times R. So this equals P1R plus P2R. So in the process of rebounding, what's going to happen is the angular momentum of the rod is going to actually be greater than what it initially started with, because this is what it started with. So we have a gain in momentum. So this angular momentum of the rod grows because of this rebound. Okay, so we can also look at this as, if we factor out the R, P1 plus P2 times R, where it hits the rod. All right, so next the ball stops after colliding with the rod. Well, if the ball stops, then P2 has to equal 0. So P2 equals 0 because its velocity is 0. Remember, this is linear momentum, mass times velocity. Now, if that's the case, and I'm looking at this equation here, then it's just going to be LR equals P1R minus P2R, but we know that this is 0, so LR just equals P1R. Okay. So if the ball stops, the angular momentum of the rod is going to be smaller in comparison to the angular momentum when it bounces. The next part, we have the ball continues along its original line of motion with less momentum. Now it's with less momentum, but it's still positive and it continues in the straight line. So this one is just going to be P1R minus P2R. Okay, they're both moving in the same direction. I know it's the difference of the two. So in comparison, the ball stopping is going to leave a greater angular momentum with a rod than if the ball actually continues along the path, because this has to be smaller. Okay. Now, if the ball sticks to the rod, right, then the ball is actually continuing in motion. It continues in a linear motion, right? So what will happen is in an angular motion, it'll stick to the rod, and then it'll start coming around, but what will happen is we are still going to get P1R minus P2R. So we get the same equation. Now, what's tricky about this, though, is we do have to be careful. So I'm kind of thinking about this very conceptually, like this would be the setup of the equation, and like I said, we could factor this out. So P1 minus P2 times R. This could be P1 minus P2 times R. We can look at it this way. The issue with this is the final velocity for the ball, right? So I have a ball that continues, right, along a straight line of motion, and I have a ball that sticks. The final velocity of the ball is not going to be the same. So even though these equations are the same, it's really easy to compare them this way because we don't have numbers. But if we did have numbers, these two would actually not be equal, right? So the question is, well, which one is going to have more velocity in comparison to the other one? And here's how you need to look at this. If the ball sticks to the rod, the total mass of my system here is the rod plus the ball, versus over here, I have the rod still separate from the ball. And what happens is with momentum, right, if you have an increase in mass, and in this case, it would be our moment of inertia, right? So our moment of inertia here for when the ball sticks to the rod, this is going to increase compared to here, where the moment of inertia does not increase. As a result, right, it is going to be harder to turn, and the velocity has to be less when the ball sticks. Okay, so we can say I of the rod increases in part D, causing a slower velocity compared to the ball in part C. Okay, so because the moment of inertia in part D, because it's increasing, it's going to slow down the velocity of the rod. And because the velocity of the rod slows down, then the ball must also slow down because it's stuck to the rod. Versus in part C, right, we have a collision, but it's going to continue in the original line of motion. So the rod is going to be able to move faster in comparison because it doesn't have the point mass stuck to the end. So in comparison, although these are close, right, and they're both the ball and the rod are still in motion, right, the ball that continues by itself is going to have more velocity than the ball that sticks.